Morning.
Morning.
Right, yeah. Okay, guys. Now, before I try to continue, any questions? Yes, guys, any questions?
No.
Good. And did you guys do the remaining questions on 89 and page 90? Okay. Any confusion there? Good. So, okay, I guess. So, what we briefly mentioned yesterday was if we said that this here is okay, was over transducer, we could say that we have what is this okay, tissue boundary. Let's just put another tissue boundary here as well. And this transducer is okay if it produces a sound wave that travels towards a tissue. That was what we call an incidence. At that tissue level, a larger portion of the energy carried by this incident sound wave here was going to get reflected. And whatever is left is going to be transmitted. Okay, guys? So we can mainly say as okay, the remaining of this chapter or this chapter here is mainly as okay going to be looking at these three things: incidence, reflections, and transmissions. Okay. Now what we did yesterday, we said okay, yes, the amount of energy that was going to be reflected back from the incidence is mainly as okay dependent upon as okay the sorry is mainly as okay dependent upon the impedance of the tissue. Clear? Okay. But let us just start talking about yes okay the incidence. Okay, but guys, is there anybody who has any questions about this? to begin with, what we mean by incidence, what we mean by transmitted, and what we mean by reflected. Yeah, okay. And as I also said that, okay, yes, this transmitted sound wave here, mainly it's okay, just becomes incidence as well, because now it's traveling towards next boundary or next tissue, where it has its own reflection. And whatever is left is going to get transmitted. But let us just talk about the incidence. So, guys, what was incidence? Okay, we can mainly say, okay, the sound wave that travels towards a tissue boundary. That will be referred to as an incidence. Yeah, okay. This incidence is okay, once it reaches the tissue boundary, it's going to strike it, and all dependent upon the impedance of that tissue boundary. A greater or lesser amount of energy carried by the incidence is going to get reflected back. Now, what you guys may have seen me doing so far is, well, okay, we said we had a transducer. We said that, okay, yes, we have a tissue boundary. And this transducer here is, okay, what it did was it produced a incident sound wave. Okay. That hits the tissue boundary at a angle. Now this angle here, guys, this is what we as, okay, in terms of geometry call, okay, as a 90-degree angle. Clear, okay? This angle, 90-degree angle, yes, okay, that can also be known as a right angle. Okay. This angle can also be called a perpendicular angle. And it can also be known as an orthogonal angle. Did you get that?
Yep.
Good. Okay. Now, if, and this is a matter of if, because it's okay, if the angle between, because it's okay, the pulse of incidence and the tissue boundary is a 90-degree angle, what we also call a right angle, what we also call, okay, a perpendicular angle, and so on, so on, so on, so. Okay. Then the incidence is referred to as normal incidence. Did that make sense? Clear? Okay. So what that mainly means is that if the angle between your incidence and the tissue boundary makes a 90-degree angle or a right angle or a perpendicular angle or an orthogonal angle, that incidence is going to be referred to as a normal incidence. Did you guys get that? So if you've been asked, okay, yes, what do you mean by normal incidence? That is going to be that when the angle between your incidence and the tissue boundary hits at a 90-degree angle. Or you can mainly say, okay, incident that hits the tissue boundary at a 90-degree angle is going to be referred to as a normal incidence. Did that make sense? Clear? Okay, so a 90-degree, yes, okay, an incident that hits, that's probably a better wording. Incidence that hits a boundary at a 90-degree angle, right angle, perpendicular angle, orthogonal angle, is going to be known as a normal incidence. Did you guys get that? Clear? Okay. Okay. And now I may say something. And a normal incidence is an ideal incidence for diagnostic imaging if you want to create an image. Okay, guys? Okay. So the right angle or the 90-degree angle or a normal incidence is the right angle. One between your incidence and the tissue. Clear? Okay. Oh, kuş. Okay. So please, that's okay. A right angle, a 90-degree angle, a perpendicular angle, or an orthogonal angle of your incidence is going to be referred to as a normal incidence. So you will hear this or you come across this term here again and again and again. But please keep in mind, guys, this normal incidence, which is mainly as okay, there's that 90-degree angle between your tissue boundary and the incidence is ideal for diagnostic imaging, where your goal mainly is okay to create an image or a picture. Is that clear?
Yes.
Okay. And that's why it's okay, we can mean it's okay, just for say, why would that be ideal? Mainly because it's okay, we know that the reflection is going to come right back. Just like, yes, okay, our mirror example the other day. Clear? Okay. That you see yourself in the mirror only if you are standing right in front of the mirror. The community says, okay, the light energy that you emit reflects directly back at you. Okay. But now what kind of other angles do we have? So we can mainly, it's okay, put our angles and say, it's okay, we can have three types of angles where, okay, yes, right angle, which was okay as 90 degrees angle. Okay, if we can have angles that are less than 90 degrees, and we can have angles that are going to be more than 90 degrees. Both of these we can say as okay, non-right angles, which are not 90 degrees, can collectively be called oblique angles. Did you guys get that? So any angle which is not a 90-degree angle will be referred to as an oblique angle. Yeah, okay. And now what we call the angles that are oblique angles and are, for instance, okay, we can just write it out, less than 90 degrees. They are going to be called acute angles. Whereas angles that are more than 90 degrees are called obtuse angles. Is that clear? Okay. Now you don't really need to just okay very much about it's okay acute angles and obtuse angles. But the main thing that you will need to know is that any non-90 degree angle or non-right angle or non-orthogonal or non-perpendicular angle or any angle which is anything but 90 degrees is going to be called an oblique angle. Okay. And that's where we mainly will say, yes, okay, if we, for instance, okay, have a tissue boundary, okay, hit by a incidence where the incidence makes any angle other than 90-degree angle. We can say, okay, here maybe yes, okay, let's just assume that this is a, let's say, okay, 60-degree angle, for instance. That this incidence here mainly because it makes an oblique angle or it hits the tissue boundary at an oblique angle is going to be referred to as an oblique incidence. Did you guys get that?
Yes.
Yeah, okay. So what two kind of incidences do we have now? We have what we call a normal incidence. What would be a normal incidence? If it hits the tissue boundary at a 90-degree angle or at a right angle. Did that make sense? Clear? Okay. Another kind of incident that we will have is going to be an oblique incidence. Clear? What would that be? Mainly as okay because it hits or it strikes the boundary at an oblique angle. Okay, and what was an oblique angle? Any angle but 90 degrees. So you can say it's okay from 89 to 0. Right, okay. And from 91 to 108 will be oblique angles. Did you guys get that? Okay, so what do we call that incidence that hits the tissue boundary at an oblique angle? What we call an oblique incidence. The incidence that hits the tissue boundary at a right angle, 90-degree angle, is called a normal incidence. Did you guys get that? Any questions about this? Okay, so guys, whenever you see the word normal incidence, there should be no question about it. What it mainly means is that this incidence here hits the tissue right at a 90 degrees. Okay, whereas, okay, you see oblique, it hits it like this, and may hit it like that. So any other angle than a 90 degree. Did you guys get that? Okay. And oh, yes, okay. In some questions, yes, okay, they may even start giving you what you want to call it. Or they may give you, yes, okay, the degree angle, but that's most likely, yes, okay, if they're talking about an oblique incidence. They may say 45 degrees, 30 degrees, 60 degrees, something like that. Okay. But the importance of those, yes, okay, we will talk more about that later on. Okay. So that was your incidence. That was your incidence. Okay. Now we can mainly, yes, okay, just say, yes, okay, what about the reflection then? Now, as I said earlier, yes, okay, mainly, yes, okay, from our mirror experiment, if that's what you want to call it. Okay, because there are some basic laws of physics that, okay, yes, applies to everything. So we can say, yes, okay. This is a tissue. We can say, yes, okay, we have a similar tissue here. We will have a oblique incidence. So we had an incidence. There's going to be some transmission. But the reflection here, right like this. Whereas, and this we can say, okay, this was where we had a normal incidence. Whereas this one here, now this is going to, yes, okay, be anything but a 90-degree angle, so that becomes, okay, yes, an oblique incidence. Is that clear? Okay. Now, there is going to be a reflection. The reflection will go like this. Yeah, okay. And, well, okay, yes, the matter about the transmission here, yes, okay, we're not going to, it's okay, going to do details now, but there will be a transmission because some of the energy is going to get reflected, some energy may be or will be transmitted. But what happens to the transmission here is pretty much, okay, going to be, yes, okay, the last topic in our, in this chapter here. Okay. But does anybody have any questions yet?
No.
Okay. So you guys good on the angles?
Yes.
Good. Let us then see. Now, transducer. And we can say it's okay. We can say it's okay. This one here is boundary 1 or tissue 1. Boundary 2 or tissue 2. And we can say it's okay, boundary 3 or tissue 3. Yep. Now what we have is we have this incidence here. Incident that is okay, travels towards the first boundary. So we can mean it says, okay, this one is going to be incidence 1. Yeah, okay. Now this incidence here is okay, it has a certain intensity. Okay, so guys, mainly for it's okay. Now what we mainly are going to do is we mainly is okay going to talk about it's okay the intensities of different waves. Yeah, okay. But as we know, that's okay. Greater the intensity, greater the power, greater the power, greater the amplitude. But just because we use the term intensity, it doesn't mean that it's not going to be relevant to the power. It doesn't mean that it's not going to be relevant to the amplitude as well. Okay. But just to simplify, so we can say, okay, this intensity here, yes, okay, or this incidence here, that's going to have, okay, yes, its own intensity. So that's going to be, yes, okay, the incidence intensity. Clear? Okay. Now, what we know is that, okay, as this incidence here is, okay, hits the boundary, a certain amount of the energy carried by the incidence is going to get reflected. So you can say, okay, this is going to be, okay, our first reflection, for instance. Okay. But just like as, okay, the intensity of the incidence was mainly as, okay, dependent upon the energy of the incidence, which was, okay, the intensity of, okay, the sound wave produced by the transducer. A greater or lesser amount of that was going to just, okay, get reflected back. Okay, but this reflection here, what is it that is going to carry? It's going to carry us, okay, a certain amount of energy. That reflection here also have its own intensity. So we're going to call that the reflection intensity. Is that clear? And now whatever was left of the incidence that was not reflected back is going to just, okay, become your transmitted intensity. Did you guys get that?
Yes.
Okay. Now, what we also, yes, okay, Ori has said that, okay, yes, this first transmission here, which is left off the first incidence after the first reflection, can also be referred to as, we can just also just, okay, call this one here our second incidence. Because I'm heading towards this, okay, the second boundary. That, okay, as when it hits the boundary here, it's okay, is going to reflect, okay, as a certain amount of energy back, and that's going to be, as okay, your second reflection. And whatever is left is going to, as okay, continue on as the transmitted. Which just becomes, okay, yes, your third incidence. Clear, okay. But what we know is that as we travel deeper and deeper and deeper, as the sound wave progresses or propagates further and further and further, its power, its intensity, its amplitude is going to get weaker and weaker and weaker. And that decrease was what we called attenuation. Okay. Now, there is a law of physics. And we mean that's okay, just going to look at that right now. And that's going to be, okay, what we call the law of conservation. Of energy. Okay. Now, what is it that the law of conservation of energy states? Well, okay, it's a law. So you can make this, okay, it's something that's made, which means, okay, talks about, okay, it's a law of energy. But what it mainly is, okay, is talking about is conservation of energy. And that mainly states that, okay, yes, says that, okay, yes, energy can't be produced or destroyed. But can change its form. But the main thing that, okay, we'll be looking at here is can't be destroyed. Now, mathematically, yes, okay, how will we prove that? That is mainly going to be proved by saying that, okay, yes, the intensity of the incidence here is always going to be equal to, yes, okay, the intensity of the reflection and the intensity of the transmission. Did that make sense?
Can you just repeat the last thing you just said, like that last sentence?
That the intensity of your incidence is always going to be equal to the sum of the intensity of the reflection and the intensity of the transmitted solid.
Yeah.
Did that make sense?
Yep, thanks.
Okay, so what did that tell us? That, well, okay, our energy is not destroyed. It's not that it's disappeared out in the blue sky. Clear? Okay. Okay. So each, you can say it's okay, milliwatt per millimeter or whatsoever of energy that you're talking about in terms of intensity, or even it's okay, each smallest fraction of energy, yes, okay, you'll be held accountable for that. Yeah, okay. Okay. Now you can just say it's okay. Use this very same example here with your money. Clear? Okay. Now you go out with, let's say it's okay, $500. Clear? Okay. Now you go to the first shop, you spend $300. You leave that shop with $200 in cash, but you got $300 worth of grocery, right? Okay. So you still have, yes, okay, if you look at it, you still have $500 worth of. Okay. Then you go to the next, okay. So now you have $200. Now you go to the next shop and you just buy, yes, okay, $50 worth. Okay. So when you leave that shop, now you have less money. You have only got $150. So on, so on, so on, so. Okay. So as you travel, yes, okay, you may say, okay, now the money that you spend on groceries, shoes, clothes, whatever other goodies, right? Okay, you can maybe say, okay, in this case, yes, okay, it's going to be equal to, yes, okay, the reflections, right? Okay, but you see that, okay, as you walk from shop to shop to shop to shop to shop, the more you shop, is okay, the thinner is it that the amount of money in your bank account or wallet is going to get. Did that make sense? So that's what we call attenuation of, yes, okay, your bank account or bank balance. Clear? Okay. But then you can come back and say, well, okay, I left the house at $500. Where the hell did they go? And then you say, okay, well, okay, $300 worth of grocery. That's okay. A nice pair of shoes that I needed. And okay, as a matching purse and this and that and so and so. Did that make sense? Okay. So each incidence, because okay, what we know is that okay, yes, the intensity of incidence 1 is going to be as okay greater than the intensity of incidence 2, which is going to be greater than the intensity of incidence 3. Okay, okay. But you can say, okay, what is going to be the difference between incidence 1 and incidence 2, or incidence 1 and transmission 1? Is going to be as okay the amount of energy that was reflected. Did you guys get that? Right. Okay. So the intensity or the incidence's intensity is always going to be equal to the sum of the intensity of the reflection and the intensity of the transmitted energy. Did that make sense? Right. Okay. So from this we can mainly, yes, okay, let's say it's okay. Incidence intensity is okay equals to the reflection intensity. plus transmission intensity. Where we may then also can say it's okay that the intensity of incidence subtracted by the intensity of the reflection. That is going to be equal to, yes, okay, that of the transmitted. Or vice versa. The intensity of the incidence being subtracted by the intensity of the transmission will be equal to, yes, okay, the intensity of the refraction. Did you guys get that?
Yeah.
Any questions?
No.
Right, okay. So you can say, yes, okay, you might be given, yes, okay, let's say a question that says the incidence of a pulsed wave is 60 watts per centimeter square. Okay. It's a boundary at an whatever angle. We can say it's okay, right angle. That doesn't really matter. Clear, okay. Two watts per centimeter square is the intensity of the reflection. And then say, okay, what is the transmitted intensity? So the only thing that you need to do here is, okay, 60 minus 2 equals 58 watts. Did that make sense?
Yeah.
Clear? Okay. They may say, well, okay, yes, you can even do it in this way and say, okay, that you give us, okay, the transmitted intensity is 13 watts, for instance, per centimeter square. Okay. After a reflection of 4 watts per centimeter square. Where is the intensity of the incidence. So what the meaning says, okay, after a reflection of 4 watts per centimeter square, you are left with 13 watts per centimeter square. And they just ask us, okay, where is your intensity of the incidence? So that's when you go and say, okay, yes, that of the incidence is going to be equal to, yes, okay, our reflection plus transmission, which is 4 plus 13, which becomes 17 watts per centimeter square. So that's math. Are you guys okay with that kind of math?
Yes, I
Yeah.
like that kind.
You may look at that pair of shoes that you bought for $300 and say, okay, well, this really worth $300. Now, who buys a pair of shoes for $300? Okay, I see some of the girls shaking their heads. No, no way. No way. Yeah, even if it was $3,000, where do you put them? You don't put them on your head, right? You still put them on your feet. So, unless somebody is okay, pull out the red carpet, then you can buy us, okay, then you can buy $3,000 shoes. Okay. Any questions, guys? Yeah, okay. But that's okay. What we will know is that that's okay. That intensity of what we just call incidence becomes lower and lower and lower and lower as the sound travels deeper and deeper and deeper and deeper and deeper. Why? Because all dependent upon us, okay, the impedance of those tissue boundaries, greater or lesser amount of energies are going to get reflected back. Okay, what we mean to call it, okay, the intensity of our incidences, which then become transmission, but it'll become a new incidence, is going to get decreased or weakened. Okay, and that was what we call attenuation. Okay. So guys, if we take it as simple and say, well, okay, we have 200 and we have to account for that. Okay, as 50 was reflected, so we are left with 150. Okay, that was simple, straightforward numbers being added up. Clear? Okay. Now, guys, you may see as okay another kind. You may as okay, if you look in your book, you may see as okay another kind of intensity of incidence. No, not incidence, sorry, reflection and transmission. And what are they? They are what we call the intensity reflection coefficient and the intensity transmission coefficient. So you guys are going to say, what the is that? And how do we do that? Or determine that? And guys, very straightforward. Okay, so, okay, but so the concept is the same, it's just okay as a little different way of looking at yes, okay, these two intensities here. But if yes, okay, once we explain what we mean by the coefficients, I hope that's okay. It will make sense. Because the bottom line is still going to be that we can say intensity of the incidence is still going to be equal to, yes, okay, the intensity of reflection added to the intensity of transmission. Okay, we said it's okay in accordance to, yes, okay, our law of conservation of energy, yes, okay, of, yes, okay, being held accountable for, yes, okay, all the energy of the incidence, we said, okay, well, the energy of the incidence is going to be equal to the sum of what was reflected back to, yes, okay, whatever was transmitted ahead. Now, guys, so that's going to be the same concept here. But here we mainly, yes, okay, we'll just say, yes, okay, the intensity of the reflection just becomes intensity reflection coefficient. Yeah, okay. And the intensity of our transmission is just going to be, yes, okay, the intensity transmission coefficient. Yeah, okay. And the sum of these is always going to be equal to 100%. So we are mainly, yes, okay, going to be, yes, okay, 100% accountable for 100% of the energy in the transmitted or in the incident view. Clear? Okay, so what is going to be the intensity reflection coefficient and the intensity transmission coefficient? We can say, okay, as far as the intensity reflection coefficient, that is just going to be the percentage of the incidence that is reflected. Or we can say, okay, the percentage of the incidence's intensity that is reflected back. Or how much percent of the energy carried by an incidence becomes a reflection that is going to be referred to as the intensity reflection coefficient. Where you then can just say, it's okay, whatever was not reflected becomes continue as, okay, as the transmission. So what is the intensity transmission coefficient going to be? Yes, okay, that is going to be the same because, okay, the percentage of the incidence that is transmitted. Or if you say it, if you don't want to say transmitted, you can say it's okay. Is not reflected. that becomes transmitted. Yeah, okay. Did you guys get that? So when we express the amount of energy of the incidence that is reflected back, but in a form of a percentage, that becomes an intensity reflection coefficient. And whatever is left is going to be as okay, what will be transmitted, but just going to be how many percent of the energy carried by the incidence is transmitted ahead, become your intensity transmission coefficients. So both of these are going to be expressed in percentages. Did you guys get that? Okay. Now, normally, guys, what they say is even yes, okay, on a great reflection, yes, okay, your reflection most likely, yes, okay, is going to be, yes, okay, 1% or less. If we just took it, okay, that your intensity of a reflection, or we can say, okay, an intensity reflection coefficient was 1%. Let's just stick with this one here, for instance. That means that, okay, 99% of the energy carried by your incidence continues as a transmission. So 1% or less, that is actually is okay. We can say it's okay, the normal range of your intensity reflection coefficient. Where we, on the other hand, can say it's okay, 99% or more is going to be as okay, your transmission intensity transmission coefficient. Of course, that's okay. It can't exceed more than 100%. But if you just said, okay, if it was 99 or 1% here, then your reflection, then your transmission, intensity transmission coefficient is going to be 99% of your incidence. Okay. Did that make sense? So again, yes, okay. Even if we, yes, okay, add these two up, plus, yes, okay, the 1%. What is it that they're going to add up to? Yes, okay. 100%. Okay. So both, yes, okay, the coefficients here are going to be as okay, not expressed. They're not going to be expressed as watts per centimeter square or watts or so on, so on, so. Your coefficients are always going to be expressed as percentages. Did you guys get that?
Yep.
So again, yes, okay. If you are given, yes, okay, an intensity reflection coefficient, okay, and they ask you to, yes, okay, calculate your transmission coefficient, you may, yes, okay, just subtract that intensity reflection coefficient from 100%. And that will give you, yes, okay, the intensity of your transmission, or vice versa. If they give you, yes, okay, the transmission coefficient and ask you to calculate the reflection coefficient, you may, yes, okay, just subtract that percentage of your transmission coefficient from 100%, and that will give you how much of the incidence's intensity was reflected back in a percentage value. Did you guys get that?
Yeah.
So pretty much here is okay. You can make this okay, just say, well, okay, here is okay. This will be 100%. And this will be 100%. Where you go and say it's okay. Coefficient. And okay, yes, that will give you the coefficient. Or likewise, coefficient, and then yes, okay, will give you the coefficient. Because your intensity, or yes, okay, your intensity coefficients, whether it's transmission, whether it is reflection, is not going to be expressed as watts per centimeter square. Okay, you will only use that when you talk about plane intensity of transmission and plane intensity of reflection. But when you go coefficients, it will become percentages. Did that make sense? Clear? Okay. So let's just take a simple example. It's okay if you go shopping again. Right, okay. And just to be simple, let's say it's okay, you have $100. Okay. The first shop you go into, yes, okay, you spend $20. Which become, yes, okay, we can say it's okay in this context will become, yes, okay, your reflection. Because the money that you had is okay, you convert it into something else. Buy a nice pair of whatsoever. Yeah. Okay. But then you can say, well, okay, how much of the money did I spend? Or how much percent of the money that I started off with did I spend? Well, you had $100, you spent $20, so you spent 20%. So you're left with 80% of the money that you started off with, right? Which you mean, yes, okay, just can carry with you to, yes, okay, to the next shop or stall or booth or whatsoever. Did that make sense? Okay, so you say, okay, I spent $20 out of $100, but when we talk about that in percentages, it becomes 20%. Clear? Okay. Now, if you had $200 to start with, and you spend $20 at the first store, that would not be spending 20%, right? That would just be 10%. So although, yes, okay, you spend the same $20, but that's just going to be 10% of what you started with. Clear? Okay. But you're going to be walking away with, okay, yes, 20% worth of material stuff, but $180 in your wallet. But that $180 is just going to be 90% off the $200 that you started off with. Okay, so but that 10% and 90% still adds up to become 100%. Did you guys get that? Get any questions? So guys, please, please, please keep your eyes open for whether the question asks you to answer in form of an intensity coefficient or whichever, reflection transmission, or whether it asks you to answer as a intensity reflection or intensity transmission, not coefficient. Did I make myself clear? Now, guys, is there anybody who has any questions about what the difference between these two here are? Okay, so it's the same concept. Okay, but in one case, we just talk plain numbers, plain intensities. Whereas when we say it's okay, coefficients is going to be as okay, percentages of your intensities, whether transmission or whether reflection, okay, from the incidence. Did you guys get that?
Yes.
Yes.
Good. Any questions? Yeah, okay. And as I said, what will determine? You can say it's okay, your coefficient or the percentage of your amount of energy that is going to be reflected back of the incidence that is determined by the impedance of the tissues. So we can say it's okay, the greater the impedance, the greater the reflection transmission coefficient. The greater the impedance, the greater is going to be the intensity of reflection, or you can say the greater is going to be the intention reflection coefficient. So greater impedance, greater intensity reflection coefficient, which mainly will mean a greater amount of energy is going to be reflected back. Did you guys get that?
Yep. Yeah.
Good. Any questions? So we pretty much killed two birds with one stone. Or we can say, it's okay, thanks God for copy and paste. Okay, because the same concept, just okay, yes. Good. Then what I would like you guys, now what you see on page 95, you see a horrible equation on that page, right? No, you don't. Clear? Okay. Okay. But the thing that you need to know is, we can say, okay, the greater the impedance, the greater your intensity reflection coefficient. Lower impedance, lower intensity coefficient of reflection. Did
So
that make
the greater the impedance, the
greater the reflection?
greater the reflection. Okay.
Or stronger the reflection, right? Okay. Okay. Because okay, greater reflection in the sense that greater amount of energy. Okay, which will just become as okay, you can say it's okay, greater intensity of the reflection. Clear? Okay, and what I said the other day is that the greater the intensity of a reflection is, the more brighter is it that is going to, yes, okay, appear on your scan. So something that looks white on your scan or bright is because it is a strong reflection. Something that looks darker is because it is a weaker reflection. Yeah, okay. And when you say weaker reflection, it's not that that reflection is going to just okay, just not deliver a punch, but okay, it carries less energy. So stronger, weaker in the sense that okay, as the amount of energy that it carries. Okay, but whether lesser or more, ultimately, as okay, what's going to happen as okay as the sound travels, as okay at different tissue levels, it loses more or lesser degrees of energy. And that causes that the sound wave gets weaker and weaker and weaker and weaker as it travels deeper and deeper and deeper and deeper. And that increasing weakening of the sound is what we call attenuation. Did that make any sense to any of you? Okay, guys, now I'll just read on these couple of pages here. So 95, yes, okay, just read the text, plus me, yes, okay, just the point differences of impedances causes, okay, okay, we can say greater difference in impedances leads to greater or stronger reflections. Okay, this equation here, you don't need to worry about it. Okay, so although you see it, you don't see it. Okay. Okay, but there are some nice questions on page 94 that I would like you guys to do in the meantime. And, well, okay, 5 small questions on page 96. So would it be fair enough that you can read on these couple of pages here while sipping off your coffee and try to answer these, that's okay, 7 questions, 2 on 94 and 5 on 96. And I see you guys back at 35. Have fun. And any questions? Jesus. No questions? That's boring, guys. Okay. And let's just see if we can answer these questions and play a little around with the questions to make some other questions. Does that sound more like it?
Sounds good.
Sounds good. Okay, thank you. Okay, guys, so we are on page 94, and we look at question number 1. So a sound wave with an intensity of 50 watts per centimeter square strikes at tissue or strikes a boundary. So what do you get from that? That the main is okay gave was okay as the intensity of the incidence. Now it doesn't tell you that this is the incidence in the wording of the question, but you get that info from saying it's okay that it strikes a boundary. Okay, okay, but when the intensity was okay as 50 watts per centimeter square. Okay, and it's totally reflected. Right, okay. Now, what they ask you here is, what is the intensity reflection coefficient? What is the intensity reflection coefficient? Now, if you say it's okay, totally reflected, I mean it's okay, all of it is reflected. But your intensity to a coefficient or intensity reflection coefficient, mainly because they ask about the coefficient that's going to be as okay, a percentage. And that mainly mean that okay, it's going to be 100% of it. Clear? Did that make sense?
Yes.
Good. Now the same question, Ali says, okay, the question had read something like that, okay, as a wave with an intensity of 50 watts per centimeter square strikes a boundary and is totally reflected. But if they then had changed, okay, as what is the intensity of the reflection? So if I said, okay, what is going to be, it's okay, the intensity of the reflection. No coefficients and so on, so yes, okay, then that what I mean. You have 50 watts per centimeter square. Did that make sense?
Yes.
Okay. Same question, but had this, okay, in the last sentence is, okay, what is the transmission coefficient? Of course, that's okay. If 100% of it is reflected back, then you will say, okay, that would be 0%. Or if they ask you, it's okay, what is the intensity of your transmission? Then that was going to be, it's okay, 0. 0 watts per centimeter square. Clear? Oh, okay, shit. Okay. So what we mean is, okay, just answer here what they is okay asking in the second question. Let us just play a little around because we can see. let's just do this. And we can say it's okay now again. Yes, okay. Let's just say it's okay that we have the incidence intensity is, let's just okay stick at 50 watts per centimeter square. Is that clear? Okay. So our question was read, okay, at the sound areas, okay, with an intensity of 50 centimeter per square strikes a boundary, which mainly is okay by the wording. You should know, understand that they are talking about the intensity, or we are talking about the incidence, and it has given us an intensity. Clear? Okay. Now, what they may say, or what we can say is okay. 20% of it is reflected at the boundary. Now, question number one could be, what is the intensity transmitted coefficient? Yeah, okay. And that's where we mainly simply say that, okay, now for that you have to, yes, okay, say that, okay, yes, or your intensity is okay, of the incidence is okay, we take that as 100%. So mainly says, okay, 100%, from which we subtract 20%, that would give us, okay, as the intensity transmission coefficient, which is going to be 80%. Did you guys get that? Did you guys get that?
Yes.
Yes.
Good. Okay. Now, if we check the same numbers here and say, yes, okay, that incidence in the intensity of the incidence is 50 watts per centimeter square. Where they mean says, okay, 20% of it is going to be reflected at the boundary. But if they now ask us that what is the reflected intensity? Yes, guys. Would anybody know how to do that?
Can you put it back up?
Yeah, no problem.
Thank you.
It's here, but it's just a matter. Are you able to read it there? So yes, okay, this is your scenario, but now we're just going to answer the green question, which is what's going to be as okay, the reflected intensity. So the intensity of your,
Is it 30?
okay, I don't know on top of my head, but we can see. So Teresa, you said 30 watt.
30 watts per centimeter square.
Okay.
I think it's 10 is what I got.
You got 10.
I also got 10.
You also got 10. Teresa, you're getting in the minority now here.
Maybe I'm just looking at the wrong transmitted number. I'm
No, my
subtracting
dear,
the
listen,
minus
okay,
50.
listen, okay. The incidences are, the intensity of the incidence was 50 watts per centimeter square. Clear, okay? 20% of that is reflected. What we are asking you, I'm asking you, so what is your intensity of the reflection? Listen, guys, this is how you will do it. Okay? Okay. So we have 50 watts. Where we say is okay, 20% of that is going to be reflected. And you mean yes, okay, just we'll divide that by 100. So 50 multiplied by 20, that becomes 1,000 divided by 100. Is 10. So yes, okay, it's going to be yes, okay, 10 watts per centimeter square. Did you get that?
Yeah, I understand it. Thank you.
Yeah, okay. Now the same data as okay, is 50 watts per centimeter square. That was your incidence's intensity. And it gave you as okay the incidence coefficient, or as okay, incidence reflection coefficient as 20%. But then asked us as okay, what is the intensity transmission coefficient? Now you can say, well, okay, when your reflection coefficient is 20%, oh, sorry, not your coefficient, intensity of the transmission. Okay, you can say it's okay, your coefficient would have been 80% of the initial intensity, 50, which you then, okay, then go. Okay, and that's where you can mainly say, okay, 50 multiplied by 80, that becomes 4,000. Clear? Okay, divided by 100, baby, means, okay. So that's going to be as okay, the intensity of your transmission. Did that make sense? And again, you can say it's okay when you add this to this, you get this. Clear? Okay. Okay. You add the percentages, yes, okay, you get 100%. Or you can say it's okay, the difference of this to this gives you this. Or if they're giving you, okay, your intensity reflection coefficient and ask you to calculate the reflection coefficient, then you just subtract this from this, will give you this. Okay, but please, okay, guys, so this is how you will do it. If you're giving us, okay, the percentage of a certain thing, which number is here, and is asking to calculate, okay, how much will it be numerically? So you can take any intensities in whatever form you want to. Okay. Or yes, okay, coefficients of yes, okay, certain intensities, and then say, okay, what is going to be yes, okay, the intensity of the other kind of intensity, or what's going to be yes, okay, the coefficients. Okay. But if you are giving yes, okay, for instance, yes, okay, an IRC, or reflection coefficient, and you're asked yes, okay, calculate what the transmission coefficient is, you mean is okay, we just subtract this percentage here from 100. Or if you are given a transmission coefficient and you're asked, okay, yes, what is the reflection coefficient? So okay, that is just going to be that you subtract this from 100. Okay. But if you are given, yes, okay, intensity reflection coefficient, clear, okay, and are asked, yes, okay, based on an incidence of XYZ amount of watts, what is going to be as okay, the intensity of your transmission. You will multiply that by the incidence and divide that whole thing by 100. That will give you the intensity of your transmission. Likewise, for your reflection coefficient, if you are given that of an intensity of the incidence, you multiply those two and divide that by 100, and that will give you okay, the intensity of your reflection. Did that make sense? So not just here, yes, okay, even if you look at, okay, yes, you say, well, okay, there's anything on, yes, okay, which is 30% off. Its original price was $50. But if it is 30% off, your question will be, yes, okay, how much money would I have to take off the original price? That's how you calculate that amount as well. So guys, okay, from now on, okay. Okay. So you come up with, okay, an amount, and that's going to, yes, okay, be what you will save off that item, which is 30% off. But here's, okay, we just calculate the percentage of a certain value. That's okay. But mainly it's okay, we'll say, okay, if this was our initial, and we take this much percent off, what is that percentage going to be as a numerical value in a plane intensity? Clear? Okay, but when they ask about is, okay, coefficient, it's going to be plane percentages. So we can go the other way around and say, it's okay, if we have, for instance, okay, an incidence of 45 watts per centimeter squared. Did that make sense? Okay. The intensity reflection coefficient is 5%. And we say, yes, okay, what is the intensity of the reflection, for instance? Okay, so how do we do that? This 45 here is going to be multiplied by 5. And then it's okay, divided by 100. Okay, so what do you get? 45 times 5 is
225. Oh,
225, right? Okay, divided by 100, which just becomes 2.25 watts per centimeter squared. Yeah, okay. Now, even though, yes, okay, this was the numbers that you were given, and they may just ask you, yes, okay, for instance, what is the transmission or transmitted coefficient? Now, that is going to be straightforward, because for that, you mean, yes, okay, just will have to subtract 5% from 100%. Or from 100, which gives you 95%. Did that make sense? Right, okay. But even if you, for instance, only was given this data here, this was your data that you got, and they then ask, yes, okay, what is the intensity transmission coefficient. Oh, sorry, not transmission coefficient. Intensity of your transmitter or transmitted intensity. Okay. Now you can do it two ways. You can say, okay, what is 95% of 45? Okay, so you could actually say, okay, based on that data, well, okay, you got the 95% from it, okay, subtracting this from 100%. But then you just use this 45% to, yes, okay, to calculate this. Yeah, okay, so that can be done in two ways. You can say, okay, either we use the 95% multiplied by 45, which was this. And okay, I should divide it by 100. Whatever that gives you, yes, okay, that is going to be the intensity of your reflection. Or you can say, well, okay, yes, based on this data here, I calculated that my transmission, reflected intensity was 2.25 watts per centimeter square. So you mean is okay, just subtract this 2.25 from your 45. It gives you is okay, 42.75 watts per centimeter square. So whichever way you want to do it. Did you guys get that? Okay. But please, 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 please keep your eyes open for whether it asks about a coefficient that has a transmission or reflection or plane intensities. Did I make myself clear, girls? And the gentleman is clear as well?
Yeah.
Okay, guys, let's look at 96 or page 96, sorry. Anybody try to answer these questions here?
Yeah.
Good. So question number one reads, a pulse of ultrasound is propagating in soft tissues such as liver. Okay, good. The pulse strikes a boundary with a different soft tissue at a normal incidence. What portion of the intensity is reflected back to the transducer and why? Okay. Now, usually it's okay. You're not going to get these kind of questions on your boards or whatever, or even not on your question, because this is an open-ended question. Okay. Okay. But what it mainly says, okay, is that it strikes the boundary between a different soft tissue. Okay, but we can say it's okay. Now there's going to be as okay, slight difference in the impedance. Yeah, okay, and due to that slighter or lesser difference in the impedance, there's going to be as okay a weak reflection. Okay. Question number 2. sound is traveling in a medium and strikes the boundary at a normal incidence. So what do you understand by a normal incidence? What did we mean by a normal incidence?
$90 degrees.
Who said that?
Teresa.
Exactly, very good, dear. At a 90-degree angle. Clear? Okay. Okay. 63%, okay, 63% of the wave's intensity is reflected back towards the transducer. What is the percentage transmitted? Or what percentage is transmitted? So it says, okay, 63% is reflected. Clear? Okay. Okay. This mainly is okay. So this 63% here is okay. What is that? If that is reflected, that is mainly is okay, just your intensity reflection coefficient. And what they mainly is okay, just ask us is okay, yes. What is transmitted? The mainly is okay, even is okay, what percentage is transmitted? Clear? Okay. And that's mainly is okay, we just say, well, okay, 63 is going to be okay, subtracted from 100%. And yes, okay, what we get is, what do we get?
37.
37%. Yeah, okay. And they ask us, okay, what is the intensity of the transmission here? Yes, okay, we don't know because they haven't given us any intensity of the incidence. They just gave us an angle, right? Or not even in numbers, but in words. Yeah, okay. Question number, okay, number 3. So what do we have is, okay, a pulse of ultrasound is propagating in bone and strike the interface of a soft tissue at 90 degrees. Now a giant reflection is created. Okay. From these facts alone, what can be said about the impedance of the bone? Clear? Okay. Now what can be said is that, okay, it has a greater impedance than that of the soft tissue, or there's going to be, okay, a greater difference in the impedance between bone and soft tissue. Okay, what can be said about the impedance of the soft tissue? Well, okay, the same. Okay. What can be said about the differences between the impedances of the bone and soft tissue? And mainly because, okay, it gives you a giant reflection. That will mainly mean that there's going to be, okay, a great difference in the impedances between the two tissues. Did that make sense?
Yeah.
Good. Question number 9, or 4, sorry. Now, sound strikes a boundary between two media orthogonally. Now, if you don't know that, okay, yes, the orthogonal, also what we call, sorry, a 90-degree angle, you will be lost in translation. Clear? Okay. Did that make sense? So please make sure that you know that, okay, yes, a right degree angle or a 90-degree angle can also be called an orthogonal angle or perpendicularly. So a perpendicular angle. Clear? Okay. So this is an example where you see that, okay, yes, the traditional term 90-degree angle or right angle or normal incidence is replaced by a synonym. Did you guys get that?
Yes.
Good. Although the media are very different, no reflection is created. Clear? Okay. And the reason for this here is that, okay, as although it is different media, now they may have different speeds. Now different media, yes, okay, may, or yes, okay, will have different speeds. But not necessarily different impedances. Yeah. So that's the explanation of why we don't have what you want to call it, a reflection here. Okay. Did that make sense?
Yep.
Yeah, okay. So please keep that in mind because that's why SOK will be SOK. Okay. So the difference of impedances. Please, guys, different in impedance. That is what leads to reflection. Whereas, okay, as difference in speed. Yes, okay, what that will lead to, we will talk about that after lunch. Did you guys get that? Okay. Now, some of you may say, but okay, Mike, is an impedance dependent upon speed? That's okay, but that speed was okay as multiplied by density. That's what led to, yes, okay. You can say mathematically, what will become the density, impedance. Clear? Okay, so you can still have different speeds and different impedance, yes, okay, and different densities, but similar impedances. So if the impedance is the same, then you don't have reflections. At that tissue boundary. This hopefully will get clear, yes, okay, once we talk about, yes, okay, our next nightmare. Our final nightmare of this chapter here. Question number 5, which of the following terms does not belong with others? So we have a list of 4 terms, and one of them is a mismatch. Orthogonal, oblique, normal, perpendicular. And these are all, yes, okay, we can say, okay, different names of incidences. Where we says, okay, it was normal. It was also perpendicular. It was also, yes, okay, orthogonal because all these here okay meant that we had a 90-degree angle incidence or a right angle incidence, whereas the one which is a mismatch is oblique because oblique was anything but 90 degree or right angle or perpendicular angle, or as we also know it as an orthogonal angle. And what we said earlier was that, okay, as an incidence, okay, that makes a 90-degree angle, a perpendicular angle, a right angle, or an orthogonal angle with the tissue boundary is referred to as being a normal incidence. There's any incident that doesn't hit a tissue boundary at a 90-degree angle, which makes it okay as a oblique angle between the incidence and the tissue boundary, will be referred to as an oblique incidence. Did you guys get that?
Yes.
So just a game of the words. Yeah, okay. But you see, it's okay if you didn't know that a right angle also was known as a 90-degree angle, was also known as a perpendicular angle, was also known as a orthogonal angle, and we call that incidence a normal incidence. An easy question like this one here would be a nightmare. Yeah, okay. Or you will see that questions are going to just okay be using more and more and more of those nicknames as I just simply called them. So what is it that you need to do? Know that okay, as things go on under more than one name. Okay. Otherwise, a very simple question can become difficult or impossible to answer because you don't know what it's asking about, because you didn't know, you didn't understand the wording of the question, or yes, okay, you don't know that, okay, this thing here also goes under that other term. Okay. Just like, okay, what do you call a pulsed wave transducer? What could be another way name for a pulsed wave transducer?
Is it therapeutic transducer?
Pulsed wave transducer.
Oh,
Imaging transducer?
Imaging transducer. So your continuous wave transducer, my dear, that is a
therapeutic.
Yeah. Therapeutic. Or a continuous wave transducer is a therapeutic or a
Non-imaging.
non-imaging. Clear? Okay. Have you guys tried to look at the question on page 98? Nope. That's fine. We can look at them together. and play the games. See. Okay. So guys, that's okay. When you see a list of okay as synonyms or nicknames, please make sure that you yes okay start yes okay. Get the habit off. Yes okay. I should remember them as well. So we can say, okay, question, okay. Age 98, okay. And we have, okay, our first question. What did that read? Now sound is traveling from bone to soft tissue. Now the impedances of the media differ significantly. And 90% of the beam is of the beam's intensity is reflected. What percentage of the intensity is transmitted? Clear? Okay. So what they mean is, okay, it just says, okay, you have an incidence. Okay. Okay, as it hits a boundary. Okay. Although here's okay, they didn't specify the angle, but we can say it's okay that there's going to be okay a difference of the impedance between these two here. And what they mean is say that okay, yes, 90% was reflected. So the mean is okay, just ask us okay, what is going to be the percentage transmitted? So that's what you mean. Yes, okay, see 100 from which is okay, subtract or 90%, and that gives us the transmitted percent, which is going to be 10%. Did you guys get that? Now, had there in this question here is okay being given a value of okay as or intensity of the incidence. Any number. Clear? Okay. Okay. But from that number, yes, okay, you could calculate the intensity of your reflection. You can calculate the intensity of your transmission. Although you are not given the intensity of the reflection to calculate the intensity of the reflection or transmission, or vice versa. Okay, so we can take any number. Anybody want to throw a number for the intensity of your incidence?
$70.
How many?
70.
70. And you're talking watts per centimeter square, right?
Yes.
Good. It could be milliwatts, it could be kilowatts, it could be, okay. Not kilowatts. Good. So what do you want to calculate? Should we say it's okay? Intensity of reflection?
Sure.
Good. So what do we have? Now we're going to say it's okay, we had the intensity of the incident rate was 70. We multiply that by 90. And since we multiply that by the percentage here to find the value of how much would that be, it's going to be 100 or divided by 100. Okay, now here you don't really need just, okay, multiply 70 by 90. Because we can just do, yes, okay, the easy trick and say, this 0 cancels this 0, this cancel this. And the only thing that you need to do is say, okay, yes, and what is it we're left with now?
63.
7 multiplied by 9, which becomes 63. So yes, okay, that's going to be the intensity of your reflection. Now, if you got this based on the data that you have been given, right?
Right.
You could also calculate the intensity of the transmission. Now, whether you would say is okay, this is the intensity of the reflection. Clear, okay. So this or 63 here so how do you guys, okay, just subtract this, sorry, 63 here, which was the intensity of your reflection, from the 70. And that's going to give you, okay, the intensity of the transmission, which is going to be 7 watts per centimeter square. Or you want to say, well, okay, yes, 70 multiplied by 10 divided by 100. Still gives you 70. What's 7 watts? Right, okay, per centimeter square. That makes sense? Okay, so that's how you do it. Okay, let's see. Okay, let's go to the kitchen. And if somebody has some leftover from, yes, okay, the Christmas or New Year dessert, it's time to get that out now. Because we're going to, we're going to scan our desserts. Okay, a sound wave is traveling in gel O. And please, guys, it's this gel O, it's not this. This is also gel, right? Or JLO? Anybody know JLO?
Jennifer Lopez.
Jennifer Lopez. Okay. Good. Okay, let's get back to the subject. Okay. So Jello. Okay, so sound waves, okay, is traveling to Jello. Okay, passes through an interface at 90 degrees and continues to travel into whipped cream. So yes, okay, we have Jello, and then we have whipped cream. Right? And okay, yes, it travels at, okay, yes, at a 90 degree. Yeah, okay. The impedance of Jello and whipped cream are nearly identical. So yes, okay. Not exactly identical, but nearly identical. Okay, now when they say it's okay near it again, there's going to be it's okay a low difference between the impedances here. Okay. What percentage of the intensity is transmitted? So they may just are asking us what is going to be the intensity of the incidence that is going to just continue as a transmitter wave. And that's going to be 99%. Because you can say it's mainly due to the close to identical impedance. Okay, there's only going to be very, very, very small. It's 1% or less that is going to be reflected. Is that clear? So what does that tell us? The greater the difference in impedance, stronger reflection. Lesser difference in impedance, lesser difference in impedance, weaker reflection. And the weaker reflection, more energy is going to carry on as a transmitted. Stronger reflection, more or less intensity, less energy is going to continue on as a transmitted wave. Did you guys get that? Okay, guys. So this was your normal incidence. This was your normal incidence. And what mainly is happens to the sound wave when it hits a boundary where there will be a difference of impedances, you will have a reflection. Clear? Okay. The intensity of your reflection or the intensity of the transmission is going to be dependent upon the difference of the impedances. And of course, yes, the intensity of your incidence. Right, okay. So far, this was what we could talk about as with normal incidences, orthogonal incidences, perpendicular incidences, or right angle incidences, or 90-degree angle incidences. Okay. What we also said is, or what we can see. So what's going to happen to to your transmission? Because on an earlier slide, earlier today, I said, well, we will talk more of the transmission, what happens to that in case of an oblique incidence later today. And that later today is going to be after lunch. And lunch is now. Okay, guys? So make sure that you, have the energy. So should we say that I see you guys back at 12:20? Is that fair enough? Good. Have fun. Any questions before we proceed? So what we have been talking about so far, you guys are good? Good.
Yeah.
Good. So. What are we going to talk about now is going to be reflection. And then we're going to come on to transmission. Okay. If we have an oblique incidence. Is that clear? Okay. Now, guys, just to be clear, it's going to be the transmission part, which is going to be a little bit complex. Now, as far as the reflection is concerned, or an oblique incidence, we already talked about that, but let me just clarify. So, what can we say is we have a tissue boundary. Yeah, okay. That's going to be okay, what we can call a boundary, or it's okay, a tissue. A boundary between two tissues. Yeah, okay. Now, since we're talking of an oblique incidence, now why would we call it an oblique incidence? Mainly because the angle between the incidence and the angle between the tissue boundary was anything but a 90-degree angle. Let's just assume that here, yes, okay, our angle, for instance, okay, is this angle here was 30 degrees. Is that clear? And just to make a comparison, yes, okay, but a normal incidence is okay, we can still see. Okay, yes, what would that have been? All is pretty much okay, that's the same concept that applies. But here is okay, in a normal instance, this was a normal incidence, so it's okay, we had a 90-degree. And what we also saw back then was that, okay, yes, it was going to be like this. So what did that give us? That angle of reflection also is 90-degree. So that's what we are going to see here as well. But here, it's okay, it's going to be a little bit different because this will be our reflection. Where we can, but what we mainly can say is that, okay, yes, that our angle of reflection angle of reflection equals to it says, okay, the angle of incidence. Did you guys get that?
Yes.
Clear? Okay. So your angle of incidence equals the angle of reflection. But since here is okay, it is oblique, and that's why it's okay. I kept it's okay. Earlier talked about it's okay. Standing right in front of the mirror, that's when you see yourself. Whereas okay, yes, if you were standing over here, it's going to be a person that stands here who will be able to see you as the reflection of the mirror. And you standing here will be able to see him or her in the mirror. Or you see his or her reflection. Clear? Okay. But what we can say is that, okay, in this instance, okay, if our angle hits at a 30-degree angle with the tissue boundary, which is an oblique angle, well, okay, yes, even then, yes, okay, the angle of reflection is going to be 30 degrees. If we said that this angle, for instance, is, okay, was not 30, but had it been 45 degrees, then, okay, yes, your reflecting angle would also have been 45 degrees. Yeah, okay, had it been, let's just say it's okay, 80 degrees, then your angle of reflection will also have been 80 degrees. Did you guys get that? So rule number one that happens in case that we have an oblique incidence is that your angle of incidence that is going to be equal to the angle of reflection. Any doubts about that?
Nope.
Clear? Okay, guys. Now, what happens with the transmission? Now, even yes, okay, in a normal incidence, what did we say about the transmission? We said that, okay, yes, if we had a normal incidence, well, okay, yes, your transmission will be this. So, yes, okay, even that would have formed, okay, yes, a 90-degree angle, right? Okay. Even if, okay, with the tissue boundary. Did you guys get that?
Yes.
Clear?
Yep.
Okay, so that will still produce a 90-degree angle. Okay. But, when our angle of incidence is oblique, when our angle of incidence is going to be oblique, we said, okay, for instance, okay, let's do it this way. Now we say, okay, yes, okay, we have a tissue boundary. Let's say that, okay, yes, this here is your transducer. This is your incidence. Okay, just to give it a number, although it's okay, may not be geometrically correct, but we can say, okay, if this angle here is okay, is a 45 degree. Now, what we should know, okay, But it's still going to be as okay that there has to be as okay that we can say, okay, the impedance here is not equal to the impedance here. Okay, only then is it that we will have a reflection, right? But this is going to be as okay, your reflection. Okay, and what we already said, or what we should know by now, is that okay, as this produces an angle of 45 degrees. Because what we said that okay, as angle of incidence equals angle of reflection. So if this was 45 degrees, then this got to be 45 degrees as well. Clear? Did you guys get that?
Yep.
Good. Now, dear guys, there can be an instance where we mainly can say that, okay, yes, this sound wave here continues straight like this. And still will make, yes, okay, and this is going to be, yes, okay, your transmission. And still make, okay, yes, a 45-degree angle with the boundary as well. Even though we have different impedances, the difference in impedances was mainly, yes, okay, just going to cause that we got a reflection. Clear, okay? Because had we had similar impedances on both sides, that's okay, then we would not have a reflection. Are you guys clear about that?
Yep.
What does it
Good.
say in the blue? What did you write in the blue at the end of the line?
This one, transmission.
Okay, sorry, thank you.
Transmission, right? Okay. Because what happened? You are like across the tissue boundary, right? Okay. So what do you call a sound wave that crosses the tissue boundary? That's going to be a transmission, right?
Yeah, thank you.
No problem. Okay. Now, what is going to be the scenario where we mainly can say that, okay, yes, your angle of incidence is equal to the angle of transmission, which means, yes, okay, will be like this. Although, yes, okay, or oblique, although, yes, okay, our incidence is oblique. Clear, okay? So where we can say it's okay that angle of incidence is going to be the same as the angle of transmission. What is going to be the scenario where that occurs? That is mainly going to be that if we say that okay, speed of sound in this medium here is equal to the speed of sound in this medium. That's when you can say that, okay, yes, the angle of transmission or angle of incidence and angle of transmission are going to be equal when both media has the same speed of sound. Did you guys get that? But please keep in mind, yes, okay, you can still have the same speed, but different impedances. You can have different speeds, but same impedances. Did you guys get that? Okay, guys. Now, I said earlier, yes, okay, that transmission is going to be very complex. And you guys are going to say, well, okay, where in the hell is the complexity here? Well, that's why, because now we just gotta just discuss a little topic on the side. First get clear that, okay, yes, you guys understand what that means. And then we can come back and say, okay, yes, now we can implement that into the transmission angle. Okay. And guys, oh, we're probably running out of slides as well. The topic that we were talking about is going to be, now, man, let me just write that in uppercase letters. It's going to be a refraction. Please keep in mind, guys, this refraction here is not reflection. Is that clear? They may sound alike, but just okay. 2 letters makes a hell of a difference. Now, before talking into the details of this, does anybody know what a refraction is?
It's a change in the direction, isn't it?
Change in the direction, good wording. Or you can say it's okay, getting off track, right? Or diverting. Clear? Okay. Now, the example that they gave you in the book, or you see a picture of a glass with water into which they have submerged a pencil. Clear? Okay. Now, what would that pencil look like? It looks like as it is broken at the, not broken, but that it is bended at the level where it enters the water. That is due to, yes, okay, refraction of the light. That it actually is, okay, appears as your pencil is bent as it enters the water. Clear? Okay. So that is going to be the refraction. But you can mainly, yes, okay, just say, yes, okay, what will that refraction be? Deviating off track. Like, okay, or deviating off the straight line. Did you guys get that? So in ultrasound, we may have refraction. Clear? Okay, we may come across what will be referred to as a refraction of the sound wave. Clear? Now, okay, so what was the refraction? We could mainly say, guys, to be clear, yes, okay, that was going to be, we can say, it's okay, the bend Or if you don't like the word bend, you just guess, okay, deviation. Or you can say, okay, you're getting off track. Yeah, okay. So yes, okay, in your glass, and we can say, yes, okay, we have the water. Oh, let me just make that. Okay, we can say, yes, okay, we have the water. No. What is it that we have? We can say, yes, okay, the straw. Now, guys, practically, your straw is not going to bend physically, right? Okay, it's going to just, okay, travel straight down like this. But what we actually see it as is, as it has bended like this. Oh, let's make it this. Clear? Okay. And why is that? That's mainly is okay because of the refraction of the light passing at different speeds in air versus water. So it appears as being different. So if we just look here, guys, yes, okay. In this case, yes, okay, where our angle of transmission was equal to the angle of incidence, sorry, was equal to the angle of transmission. That was when we had, is okay. In this case, yes, okay, we could say that there was no refraction. And what caused that no refraction? Was in this instance, yes, okay, mainly because we had similar speeds on both sides. That this medium here and this medium here had the same propagation speeds. Although, yes, okay, our angle of incidence was oblique. Yeah, okay. So actually, it's okay. When in this instance, it's okay, will be a refraction is if our transmitted wave had gone like this, for instance. And when you then could say, yes, okay, now we have an angle that was going to be greater than 45 degrees, we could just say it's okay, 80 degrees. Did that make sense? And or yes, okay, had our incident, transmitted wave refracted like this, and we could say, yes, okay, we had a angle which now was lesser than that of the incidence. We could say, yes, okay, here for instance, okay, just 20 degrees. So what would these two here be? Okay, what would this here be? Or even, yes, okay, this one here. Both of them would be, yes, okay, angles of refraction. That it deviated off from 45 degrees to 80 degrees, or deviated off from 45 degrees to 20 degrees. Clear? Okay, that will mainly mean that, okay, yes, our beam refracted as it entered from one medium into another medium. Did you guys get that? So it can happen in both directions. The whys and so on, we're going to come to that. But so far, are you clear about that? Okay. So in your ultrasound, guys, there's going to be, as okay, two requirements. Two requirements for a refraction to occur. Okay, that it goes off, yes, okay, 45 degrees to either 80 degrees. Not necessarily, even if it's just 45 to 46, it's still a refraction. But that's okay, just as we use here as a demonstrator here, say it's okay, 45 to 80 or for 45 to 20 degrees. Because now your angle of transmission is not the same as your angle of incidence. In that case, you can say that your beam has refracted. It refracted as it enters into the different medium. So our two requirements that needs to be fulfilled for a refraction to occur. Please keep in mind, guys, not reflection, but refraction. Requirement number one is that we will need an oblique incidence. Clear? What did we mean by an oblique incidence? The incidence angle was not equal to 90 degrees. Did you guys get that?
Yes.
Good. The second requirement, please keep in mind, guys, that's okay, both requirements need to be fulfilled, is that we will need a difference in the propagation speeds between the two media. Propagation speeds. Not impedance. Did you guys get that?
Yeah.
Right? So the magical word or the magic word here is difference in the propagation speeds. So if you had difference in impedance, the only thing that we can say then is that, okay, yes, you will get a reflection. Reflection with an LE. Clear? Okay. Now, let me ask. In case of a normal incidence, do you have a refraction? Will you have a refraction in case of a normal incidence? Refraction with RA.
No.
No. Christian, do you mind tell us why?
It needs to be oblique incidence.
You need to have an oblique incidence. So you can't say, well, okay, we had different propagation speeds or we had different this or different that. Okay. Both requirements need to be fulfilled for an refraction to occur. Clear? And what are those requirements? That your incidence is oblique and that the two medias have different propagation speeds. Clear? Okay. They can have different propagation speeds, but not necessarily different impedances. So the impedances will determine or the difference in impedances will determine the reflection, how much energy is going to be reflected back, right? Whereas the difference in the speeds between the two media will determine the angle of refraction with an RA. Did you guys get that? So once you have an oblique incidence and different propagation speeds between one medium and another medium, you will have a refraction. Did I make myself clear? Good. Anybody who did not get it? Anybody who want me to repeat any of the things I just said? So you guys are clear? Good. Now, guys, again, if you go to your book, you have your books, and you go on to page 102. Do you guys see page 102? And you see a second law of, or you see a law, right? Good. And you see again, yes, okay, a horrible equation, right? Okay. And what's the good part about a horrible equation? You see it where you still don't see it, okay? That's the good part. So did he just write page 102 for nothing? Did Mr. or Mrs. Okay, I think it's a Mr. Edelman just write page 102 for nothing? Or why did he or she pump? Yes, okay, I'll put this page here in this book. Or you even talk about Snell's law. Okay, guys, now I'd say, well, okay, the equation is out. But the concept you still need to understand. Okay, and I mainly, yes, okay, just summarize the concept for my students. And just like any other badge, OMG. Just like any other badge, I will give it to you guys as well. So two things that we can see about SOK Snell's law. Okay. One is that, okay, yes, it is about refraction. So have we not had refraction, sorry. Had we not had refraction in ultrasound? Well, okay, yes, then we would not have been talking about Snell's law. Clear? Okay. But the summarizing of, okay, as the equation and or, yes, okay, the summary of this whole page here is that we can see it's okay, that's Snell's law states. And we can say it's okay, the greater the difference in the propagation speeds in true media. The greater is the angle of refraction. Okay. At least that's okay, that's how I summarized it. Okay. Then we can say it's okay, the greater the greater difference in this propagation speed in true media, the greater is going to be the angle of refraction. Yeah, okay. And let us just look at, okay, what do we mean by the angle of refraction? What does that mean? Now, let's just say that we have two media, right? Okay, we can just say, okay, the boundary is okay between the two media is here. So we may have, okay, as a media E. And we can say it's okay, we have a media B. Yeah, okay. Now, in this case here, in media A is okay, that's me, it's okay, going to be, it's okay, where our incidence will travel. And just to say it's okay, it hits the boundary at an angle of, let's just say 45 degrees. Yeah, okay. Now we can just say that, okay, yes, as well, that, okay, yes, we also have uneven impedances between the two media, and that's going to cause that, okay, yes, we will also have a reflection. And what we already said, okay, yes, that, okay, that angle of reflection is going to be equal to that of the incidence. Clear? Okay. But, what we could have said that, okay, yes, now had we had even speeds, speed in this medium was equal to the speed in this medium here. That's where we say it's okay that we don't have a reflection. So it's okay here, there's going to be no refraction. And that's why we can say that, okay, yes, the angle of the transmission or incidence and angle of transmission would have been the same. Did you guys get that? Clear? Okay. Whereas if we said that, okay, yes, that the speeds between these two media here was not the same. That's when we as okay go saying as okay, now both requirements were fulfilled. We had an oblique incidence and we had different speeds. So that's going to cause that, okay, so we will now have a refracted transmission. But we can now say that now this says, okay, in this case, okay, it made an angle which was greater than 45. We can say, okay, it made an angle of, let's say, 60 degrees with the tissue boundary. But to actually, as okay, determine what our angle of refraction is, that's when you go and say, well, okay, with no refraction, it was 45 degrees. After refraction, it was 60 degrees. So to determine, yes, okay, where will become, yes, okay, our angle of refraction, we mean, yes, okay, we'll need to subtract these two from one another. So that means in this case, it's okay, will give us that, okay, yes, our angle of refraction is 15 degrees. Maybe we can say it's okay, this here. This is the degree, or that's the angle at which, or to the extent of which, yes, okay, the beam reflected. Did you guys get that?
So if speeds are not the same, then refraction occurs.
Exactly, because then your second requirement for a refraction will occur, be fulfilled, right? Okay, we had an oblique incidence and we had different speeds.
Right.
That's what I'm told here, right? Okay, what do we need? We need an oblique incidence. What was that? Any angle of your incidence was anything but 90 degrees. But the second requirement was going to be, and both has to be fulfilled. Both has to be fulfilled for a refraction to occur. So you also have to have different speeds in the two media. And that's why we said in Snell's law that, okay, yes, the greater the difference in the propagation speed, greater is going to be the angle of refraction. Okay, so in this case, yes, okay, we can say we got a degree of refraction of 15 degrees. Clear? Okay, let's just say, yes, okay, that there was, okay, in case that we had a small difference, that there was, okay, a less difference between the two speeds here. Did that make sense?
Yeah.
Okay, a less difference. Whereas if, for instance, yes, okay, if you, for instance, okay, had a great difference in the speeds between these two medias here, okay, we might end up with, okay, as let's say, it's okay, a greater angle of refraction. Where you come in, it says, okay, now I may do something, and we says, okay, that what we just end up having is that it goes to an angle of, let's say, it's okay, 5 degrees. Where you may say, okay, now what's going to be our angle of refraction here? That's when you say, okay, you subtract 5 from 55. So our angle of refraction in this case, it would have been 40 degrees. Okay, but that's going to be as okay when there will be as okay a great difference in the speed between the two medias, that we actually as okay will have a greater angle of refraction, which in this case here was 40 degrees. Did you guys get that? Okay, okay. But your angle of reflection, refraction with an RE. Maybe yes, okay, just account, well, okay, if I'm going like this and refract like this, that would be a greater angle. As compared to, okay, if I'm going like this and just refract like this, that would be a lower angle. Okay, so angle of refraction only accounts for us, okay, how many degrees is it that I deviate off track? Did that make sense? Whereas, okay, if I don't deviate, yes, okay, I just go in a straight line. I'll continue, yes, okay, as I went, or as I was going before. Okay, but yes, okay, this is a slight refraction, this is a greater refraction. Any questions? We're not done with the refraction yet. There's more, okay, there are more feathers to pick. But guys, is there anybody who has any questions about Snell's law? Nope. Good. Oh. So where does the refraction occurs? It occurs in the transmission. Here, okay. Now, guys, this is an important topic. And you will realize that in chapter 22. Oh, sorry, 21, sorry. Because in chapter 21, there's going to be a topic called refraction, which is an artifact. A fakie on your ultrasound image. Okay, so what would be my first question at that point? Even before starting talking about refraction. What is a refraction and what are the requirements for a refraction, right? What are the requirements for a refraction? What are the requirements for a refraction to occur? Not reflection, refraction with an RE.
Oblique incidence and different propagation speeds.
Exactly. Okay, so you don't have refractions in normal incidences. Clear? Okay. You may have reflections and so and so, but no refractions because a normal incident will mean that, okay, that's okay. What we label here as the first requirement has not been fulfilled. You may have different speeds, but that is not going to be able to cause a refraction itself. It has to be both of them. Okay, so both of them has to be tick marked to cause a refraction with an RA. Did you guys get that? Good. Now let's see if we can, yes, okay, close this whole discussion here with one stone. So we may say as okay, media A, media B. Yeah, okay. Now in media A, what do we have? Oblique incidence. And okay, yes, let's just do it this way. And we can see. So the other example is going to be again media A, media B, again here. This, we can say media A and media B. And in all three is okay, just not to make too much confusion about it, because probably it's okay, say supposedly it's okay, we have the same angle of incidence. And we can just say it's okay, keep it in the middle. Forty-five degrees. Is that clear? Okay. Now, what we may say is that, okay, as far as the speeds are concerned, here we have, because it's okay, 1,000 meters per second. And okay, yes, oh, let's try it up here again. 1,000 meters per second. Yeah, okay. So what we will have, the transmission, there's going to be no refraction. Or this angle here is also going to be 45 degrees. Clear? Okay, now although it's okay, we had an oblique incidence, but the reason that we don't have a refraction was because that the speeds were the same. Did you guys get that?
Yes.
Okay, but although having SOK different or same speeds, we can still have different impedances, which is okay, still were called okay as a reflection. Where this angle will also be 45 degrees. Now, just to compare, because I want to kill a lot of birds with one stone. Let's just say that, okay, these here is okay, mainly indicate, okay, that's 45 degrees. Okay. Now, what we may say is, okay, over here, then we, for instance, okay, have a speed of, let's say, okay, 1,000 meters per second in medium A. And let's say it's okay, 4,500 meters per second in medium B. Now we're going to get more specific, okay? Because what we will end up with, we can say is okay. Then now because of different speeds, both requirements are fulfilled, we will have an oblique incidence that we have different speeds. Because one medium, yes, okay, the sound travels at 1,000 meters per second. Air travels at 4,500 meters per second. So both requirements are fulfilled, and that will mean, yes, okay, mean that now, yes, okay, we will have a refracted wave that's going to deviate off and not be 45 degrees. Here we can see it's okay, it actually is okay, deviates and goes like, and make a 90-degree angle with the medium. Yeah, okay, but what we still can say is, okay, that our angle of refraction still is going to be as, okay, the difference between 45 and 90, which is 45 degrees. Is that clear?
Yes.
Good. Let us just go down here then and say, it's okay, now what do we have as the speeds here? Okay. Now we can say, it's okay, in this medium here, it's okay, we still say, it's okay, in our incidence medium, it's okay, we still have, it's okay, let's say 1,000 meters per second. Where here is okay, in the second medium here is okay, it's still going to be as okay at different speed, and that will mean yes, okay, still lead to yes, okay, that we will have a refraction. But let's just say that okay, as in this instance here, is okay, our speed in the second medium, in medium B maybe. Let's just say it's okay, 200 meters per second. Did you guys get that?
Yes.
Good. Clear? Okay. And now we're going to have a wave that is going to be refracted, so it's going to mean that it will not be 45 degrees. It may go greater or lesser. But it's okay, here we go. Let's say like this. And let's just say that it went from 45 degrees to, yes, okay, make an angle of, let's say it's okay, 35 degrees. So in this case, here is okay, our the angle by which it refracted off is just going to be 10 degrees. Did you guys get that? So it does, in this case, yes, okay, just divide off by a angle of 10 degrees. Any questions? Now, how did I kill a lot of birds with one stone? because I made this okay, brought all your okay last couple of pages into one slide. Your Snell's law, your refractions, your difference of speeds, bum bum bum, bim 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 bum bum. And what's the last things that we need to talk about? So yes, okay. We can say it's okay. In example A, what did we have? But okay, we had the oblique incidence, but since we had the same speeds, no refraction. Right?
Right.
Good. In B, now what is the information that we got from B? Well, okay, yes, we have an oblique incidence and we have, yes, okay, a difference in speed. So since we have a difference in speed, both requirements were fulfilled for a refraction to occur. Clear? Okay. Of the numerics, all right, okay. We mainly says, okay, that in this case, yes, okay, our angle or our beam deviated off an angle of or refracted by an angle of 45 degrees because it went from 45 degrees to 90 degrees. Clear? Okay. So that's how much it deviated, how much it refracted. Where here in C, still, yes, okay, we have the oblique incidence. We also have, yes, okay, the different speeds. But here we see that, okay, yes, it only deviated off by an angle of 10 degrees. Clear? Okay. So why? Why here 45 degrees and why here 10 degrees? Because in accordance to Snell's law, what we see here is that, okay, yes, the difference between the two speeds here is lesser, whereas over here, the difference between the two speeds is greater, right? So what does Snell's law say? That if you have a greater difference of speed here, okay, you can just do it and say, well, okay, here the difference of the speed, that was actually, that's okay, 3,500 meters per second, right? Where here we only had a difference of speed, which was 800 meters per second. Clear? So what does Snell's law say? The greater the difference in the propagation speed, the greater the angle, which may mean the lesser the difference in the propagation speed, lesser will be the angle of refraction. Did you guys get that?
Yes.
Good. Now, some of you will say, Mike, or your question may arise, but Mike, why couldn't we have got from a 45 degrees to a 0 degree angle here? Or from a 45 degrees to a 50 degrees angle here? And still have, okay, yes, an angle of refraction of 10 degrees. Yeah, sure, no doubt about that. So what dictates that, okay, here is going to be as okay, a lesser angle than it was over here? Or here is okay that your angle of transmission is going to be greater than the angle of incidence. And the thing that dictates that is, now it's not written directly in the book. If it is, then okay, peace be with that, but I'm going to give it out as a cheat. And just remember that the medium with the greatest speed will have a greater angle a medium with a lower speed will have a lesser angle. That's pretty much all that you need to loggy or know for the questions in your exercise. Or you can say, it's okay, not the loggy, but the cheat of what to loggy, or the cheat that you need to know.
Can you just repeat that one more time?
Good, no problem. The medium with the greater speed will have a greater angle. And a medium with a lower speed has a lesser angle. And isn't that what we saw here? Well, okay, I hear the speed. Oh, sorry. In A, well, okay, same speed, so that's okay, no refraction, right? Here.
Yep.
Okay. The reason that medium B in this case has okay had a 90-degree angle and not a 0-degree angle was because mainly it's okay when you compare the speeds between the two media here and here. It's okay, medium B, that was the medium which has the higher of the two speeds, right? So that's why we have a greater angle compared to this one, or compared to your incidence. Did you get that, Maria?
Yep. Thank you.
Okay, whereas if you go to C, no, thank you. You go to C, well, okay, oblique incidence, okay, we got that one. Clear, okay? Okay, we got a refraction. But why wasn't it that, okay, yes, it didn't went on to 55-degree, which would still have been an angle of refraction of 10 degrees. But went from, yes, okay, 45 to 35 degrees. Was mainly because, okay, in this medium here, okay, where we had the transmission, it had a lower speed compared to the medium where we had the incidence, which had a greater speed. So medium with greater speed, greater angle, medium with lower speed, lesser angle. Medium with lower speed, lower angle, medium with greater speed, greater angle. A medium with same speeds, well, okay, yes, although, yes, okay, we had an oblique incidence, but the angles would be the same because there would be no refraction. Clear? Okay. Did that make sense?
Yes. Thank you.
Yes, guys. That was your chapter number 6. Yes. So where are we? Yes, okay, we have covered quarter of the chapters. Okay. Oh, you bought a jacket. Oh, doctor jacket, wow. Okay, guys. Now I think that, okay, yes, at the end of this chapter here is, okay, we got a total of 16 questions. Okay. And usually that's okay. Most students have issues with the last 9 questions. Should we look at them together? Okay, just one thing, guys. I'm gonna add our slides now, so the system is not going to. Although here, yes, okay. I said this was medium A, this was medium B. But that's okay. In your questions, that's okay. They may say, that's okay. Put this one here as medium 2. And this one here is 1. Or this one here as B and this one here as A. So that's okay. You gotta be as okay watching out for things like that. Okay. You know what, guys? CAID. If anybody is able to, yes, okay, guess what this secret agency stands for, yes, okay, you'll be good. CAID.
I call it a day.
Here you go. Okay, just revise the material that we talked about. Just revise the material that we talked about, okay? I think, okay, it went faster than I thought. That's okay, I ran out of slides, so Zoom is not allowing me to go on to 21. I'm stuck in my 20s, or I'm stuck at 20. So, okay, but yes, okay, tomorrow, what will we be doing? Well, okay, and not only, yes, okay, these questions here, but there's probably also going to be, okay, a whole bunch of paired questions that's okay in the back of the book. Yeah, okay. So if you really want to just, okay, polish up on all the concepts that we have talked about in this chapter here, it's okay. Try not to be absent tomorrow. Okay, guys? Okay, God bless. And unless somebody has a last word, a question, something that you want me to repeat because it got lost in translation. Snell's law, good. Law of conservation of energy. The difference between plane intensity and intensity coefficients. How to calculate a coefficient, or that says, okay, an intensity by having the coefficients and our initial intensity. You guys good on those? Okay, then you're good for the next quiz. Okay. Nah, it's not just going to be chapter 6. Let's do some more. Okay. Okay, guys. But yes, okay, tomorrow, yes, okay, we'll try to just, okay, do as many of the questions as possible. So please try to just, okay, revise the material. Okay, guys? Okay. Enjoy the day. And see you guys tomorrow.
I see.
Okay, God bless.
See you.
Okay,
Bye.
bye-bye. Bye-bye.